Evaluate limits of radical and exponential functions at infinity. So first off, we need to look at limits at infinity of rational functions that have radicals in them. So we have radicals inside of rationals, which, kind of complicates things a little bit. So to help uncomplicate that, we need to review some skills here, such as how do we factor variables from a radical expression. And we're going to take a look at this first example here. We want to take the square root of 3x squared plus 6. We want to factor out the highest degree variable that we can. So since we're dealing with a square root here, we want to look for, okay, what's the highest variable that has an even power that we can factor out? And in this case, it's pretty simple. We have an x squared, so we're going to try to factor out an x squared. So, just like we did with factoring before, we're just going to divide x squared from both of the terms inside the radical. So this is going to become the radical of x squared times 3 plus 6 over x squared. And then since we have multiplication inside the radical, we know that we can pull that apart to be two separate radicals. This is going to become the square root of x squared times the square root of 3 plus 6 over x squared. Alright, so there's not much we can really do with 3 plus the square root of x squared because that's two terms being added in a radical. And we can't pull apart a radical when it's addition. So we can look at the square root of x squared term here. And we know that we can take the square root of x squared because x squared is a perfect square. However, remember, whenever we take the square root of a variable, there's always the plus or minus option here. So, while the squared and the square root will cancel out, that's going to leave us with a plus or a minus x. And that's going to be multiplied by the square root of 3 plus 6 over x squared. Now this plus or minus aspect of the x variable in the front is a little bit peculiar. How can we have both a positive and a negative version of that? Well, moving forward, depending on the limit that we're trying to evaluate, that'll determine whether or not we want to use the plus or minus x. Another way we can rewrite the plus or minus x to maybe make ourselves feel a little bit more comfortable is we can rewrite it as the absolute value of the square root of 3 plus 6 over x squared. Because remember, square root of x, we have the positive and the negative portion of that. Alright, so there we go. We have factored out something from the radical. Now we're going to do the same thing with letter b. Again, since it's the square root, we're looking for powers of 2. And here we do have an x squared, so just like before, with letter a, we're going to factor out that x squared. So we'll have the square root of x squared times the quantity 4 plus 5 over x squared. And just like before, since it's multiplication, we can pull the radical apart to make it the square root of x squared times the square root of 4 plus 5 over x squared. And then just like before, the square root and the squared will cancel out, but that's going to leave us with a positive or a negative x value times the square root of 4 plus 5 over x squared. And again, if that plus or minus x in the front is making us feel a little bit uncomfortable, a little bit unsure, remember we can always rewrite it as the absolute value of x times the square root of 4 plus 5 over x squared. Boom, factored. Moving on to letter C, here we have the square root of 25x cubed minus 3x minus 3. Now in this case, we have an x to the third power. And unfortunately, 3 is not even. So we're going to have to do something a little bit different here for this particular radical expression. Because we don't want to factor out an x cubed, because we can't take the square root of x cubed easily. Can we do it? Yes, but it's not as simple as we would like. So, since we can't factor out an x cubed, let's just go down a little bit and let's factor out an x squared. Because x squared is even. And that's going to leave us with 25x minus 3 over x minus 3 over x squared. Again, since this is multiplication, we can break this apart into two separate radicals to be the square root of x squared times the square root of 25x minus 3 over x minus 3 over x squared. And as we've done before, the square root of x squared is going to be plus or minus x times the square root of 25x minus 3x squared minus 25x minus 3 over x minus 3x squared. And as always, we can rewrite it as the absolute value of x if we want, times the square root of 25x minus 3 over x minus 3 over x squared. Boom. Factored. So we're not always going to get this nice and neat whole number at the beginning. Sometimes we might be given expressions that we need to keep part of the variable inside the radical because we can't factor it out. All right, let's move on to our last example here. We have the square root of 49x to the fourth plus x squared plus 2. And here our largest variable is x to the fourth. Just so happens that x to the fourth is even. So therefore, we can factor it out of the square root function. So that means we can rewrite this as the square root of x to the fourth times, and that's a bad times, let's try that again, times, a little bit better, not great, the quantity 49 plus 1 over x squared plus 2 over x to the fourth. And then, just like we've been doing, we can break this apart because it is multiplication. So we can get the square root of x to the fourth times the square root of 49 plus 1 over x squared plus 2 over x to the fourth. All right, then finally we want to simplify x to the fourth. So let's just take a moment here, and let's come over to the side and let's look at this. So we have the square root of x to the fourth. Now, if we take the square root of it, we are going to end up with x squared. But then the question is, well, whenever we take the square root of a variable, we need the plus or minus sign, which is kind of true, but not in all situations. We are not going to need this. We're not going to need the plus or minus sign here because we have x squared. And x squared is interesting because with any value of x that we plug into x squared, we're always going to get a positive number because whenever we square something, it becomes positive. So, since we have that x squared here, we don't need the plus or minus because this x squared term will always be positive since it's squared. So when we come and we simplify x to the fourth in our problem here, we're just going to end up with x squared times the square root of 49 plus 1 over x squared plus 2 over x to the fourth. And that is factored again because x squared will always, always, always be positive since it's squared. All right, so now that we have that skill reviewed, let's go dive in and look at our limit at infinity of a radical inside of a rational function. So here we're given the example limit as x approaches infinity of the square root of 3x squared plus 6 all over 5 minus 2x. And we're going to evaluate this the same way as we did when we evaluated the limits of infinity of rational functions. We want to factor out the highest degree in the numerator, and we want to factor out the highest degree in the denominator. It's just here the problem is, how do we factor out the highest degree in a radical? Well, we just reviewed that skill, so we can dive in and get to work. We can see here that we have the x squared is the highest degree inside the square root, and x squared happens to be even, so that plays nicely with the square root. So we can go ahead and we can factor out an x squared, so we're going to have the limit as x approaches infinity of the square root of x squared times 3 plus 6 over x squared. All right, so now we just need to look at the denominator. What is the highest degree variable in the denominator? Well, it happens to be x. So we can factor out an x, and that's going to leave us with 5 over x minus 2. Well, now we can continue our simplification here, so we're going to be left with the limit as x approaches infinity. I can pull apart the radical in the numerator because it's being held together by multiplication to get x squared times the square root of 3 plus 6 over x squared. That's all going to be over x times 5 over x minus 2. Alright, now we can simplify the square root of x squared. So this is going to give us the limit as x approaches infinity of plus or minus x times the square root of 3 plus 6 over x squared all over x times 5 over x minus 2. Alright, then the next thing we need to look at is this whole plus or minus x here. Whoa, what happened there? Is the plus or minus x. Which version of the x we're going to use? Are we going to use the positive x or the negative x? Well, since we're looking at the limit as x approaches positive infinity, all the x values here are going to be positive, which means we're going to be using the positive form of that x. So we're going to be left with x times the square root of 3 plus 6 over x squared all over x times 5 over x minus 2. And we can see we have a factor of x in the numerator and a factor of x in the denominator, so those will cancel out, leaving us with the limit as x approaches infinity of the square root of 3 plus 6 over x squared all over 5 over x minus 2. And just like with our limits of infinity at rational expressions and limits at infinity of polynomials, we now want to push that limit all the way through, and I'm using my totally made-up word of limification here. So we'll just limify everything, and that's going to leave us with the square root of the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 6 over x squared all over the limit as x approaches infinity of 5 over x minus the limit as x approaches infinity of 2. And then looking back, we know that if we have the limit of infinity of a number over any variable, that's going to be 0 and 0. So that's going to leave us with, let's see, the square root of the limit as x approaches infinity of 3 all over negative the limit as x approaches infinity of 2. And these are both limits of constants, and we know the limit of constant is a constant, so that's going to leave us with radical 3 over negative 2, which we can rewrite as being negative radical 3 over 2 as the value of our limit, or the intended height of the function as x approaches infinity, or the end behavior of this particular function. Alright, our next example is going to look eerily similar to our first example, with the only difference here being the fact that we're now going towards negative infinity, which means a lot of our work is going to be the same. So I'm just going to first go ahead and skip some steps. So I know that I can factor out that x squared from the radical, I can factor out the x from the denominator, so we've already done that in the last example, so we'll skip that here. And we'll go to the important step, which is going to leave us with the plus or minus x times the square root of 3 plus 6 over x squared all over, all over x times 5 over x minus 2. And then the important part here is, well, now we just have to deal with that whole plus or minus x thing. Which x are we going to use? Well, last time, when it went towards infinity, we used the positive x. Here, our x is approaching negative infinity, which means we'll use the negative x version of this. So that means we'll have the limit as x approaches infinity, as x approaches negative infinity of negative x times the square root of 3 plus 6 over x all over x times 5 over x minus 2. And we have a factor of x in the numerator, a factor of x in the denominator, so we can cancel those out again, leaving us with the limit as x approaches negative infinity of negative the square root of 3 plus 6 over x all over 5 over x minus 2. And then we can go in and we see that there is a negative in the front here, so we can actually factor that negative out of the limit so we don't have to worry about that anymore. So we're going to have negative the limit as x approaches negative infinity of the square root of 3 plus 6 over x all over 5 over x minus 2. And I said 5 over x and I wrote 2, so let's change that. Alright, well, from our last example, we already know what this expression equals. And based on the last slide, we know that that expression equals the square root of 3 over negative 2. And with the negative in the front times the negative on the inside, that's going to be positive. So the end behavior for this particular limit is going to be y equals radical 3 over 2. Or, as x approaches negative infinity, the height of the function gets closer and closer and closer to radical 3 over 2. All right, let's take a look at another example. So here we want to evaluate the limit as x approaches negative infinity of 3x minus 2 all over the square root of 4x squared plus 5. So just like before, we want to factor out the highest degree term in the numerator and factor out the highest degree term in the denominator. So we're going to have the limit as x approaches negative infinity. Highest degree variable in the numerator is x. Highest degree variable in the denominator is x squared. So let's see, we're going to have x times 3 minus 2 over x. And that's all over, let's see, the square root of x squared times the quantity 4 plus 5 over x squared. And then we can keep working here. We're going to have the limit as x approaches negative infinity of x times 3 minus 2 over x, all over the square root of x squared times the square root of 4 plus 5 over x squared. And then we can take the square root of x squared, leaving us with a plus or minus x. So x times 3 minus 2 over x all over plus or minus x times the square root of 4 minus 5 over x squared. Now, what do? Do we take the positive x or the negative x? Just like before, since our x approaches negative infinity, we're going to take the negative x. So we're going to get the limit as x approaches negative infinity of x times 3 minus 2 over x all over negative x times the square root of 4 minus 5 over x squared. And whoo, is this a lot of writing. All right, let's keep hitting it though. Factor of x in the numerator, factor of x in the denominator cancel out, leaving us the limit as x approaches negative infinity of, where'd that blue dot come from? Let's get rid of that guy. And we're going to have what? 3 minus 2 over x all over negative times the square root of 4 minus 5 over x squared. And then we can use our limit properties and apply the limit to every term. So that's going to give us the limit as x approaches negative infinity of 3 minus the limit as x approaches negative infinity of 2 over x. Oh gosh, all over. When is it going to end? Negative the square root of the limit as x approaches negative infinity of 4 minus the limit as x approaches negative infinity of 5 over x squared. Oh, all right, here we go. Let's evaluate it. Number over infinity goes to 0. Number over infinity goes to 0. Then we have the limit of a constant is just going to be the constant, so that'll be 3. Limit of a constant will just be 4. So what does that leave us with? That's going to leave us with 3 over negative square root of 4. And we know the square root of 4 is 2, so that's going to leave us with negative 3 over 2 as our end behavior. So as x approaches negative infinity, the height of this particular function is going to approach negative 3/2. All right, next up we're going to take a look at the limit as the square root of 25x cubed minus 3x minus 3 all over 3x plus 1. So let's factor out the highest degree in the numerator and the highest degree in the denominator. So in the numerator, we need to be careful because here's the case where we don't want to factor out an x cubed, because an x cubed doesn't pull out of an x squared nice and neatly. So, like we did in the beginning, we actually want to factor out an x squared. So we're going to have the limit, and that's the wrong color. We're going to have the limit as x approaches infinity, and we're going to factor out an x squared, leaving us with a 25x minus 3 over x minus 3 over x squared in the numerator. In the denominator, though, we can see that the variable with the highest degree is an x, so we'll factor out an x, leaving us with 3 plus 1 over x. All right, now we can continue getting to work. We can pull apart the radical here, so we're going to get the limit as x approaches infinity of the square root of x squared times the square root of 25x minus 3 over x minus 3 over x squared. And that's all going to be over x times 3 plus 1 over x. All right, now we can get rid of we can simplify the square root of x squared, and that's going to leave us with the limit as x approaches infinity, plus or minus x, times the square root of 25x minus 3 over x minus 3 over x squared, and then that's all over x times 3 plus 1 over x. All right, now since our x is approaching positive infinity, that means that the x we're going to choose is we are going to choose the positive form of that x. So that means we're going to be left with the limit as x approaches infinity, and boy, do I hate radicals now, because it takes so much effort to write them. And then minus 3 over x minus 3 over x squared, all over, starting to hate limits at infinity. So much writing, so many steps. All right, but now we can see we have a factor of x in the numerator, factor of x, then it on there, poof, go away. Then we can use the limit properties to go ahead and take the limit of all these terms. So that means we're going to have the square root of the limit as x approaches infinity of 25x minus the limit as x approaches infinity of 3 over x minus the limit as x approaches infinity of 3 over x squared, all over the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 1 over x. Now we know the limit at infinity of a number over a variable is going to be 0, so we can go ahead and we can eliminate those out. And that's going to leave us with the square root of the limit as x approaches infinity of 25x, all over the limit as x approaches infinity of 3. And then on the inside of the radical, we can use direct substitution, so that's going to be 25 times infinity over, and remember the limit of a constant is a constant, so that'll be 3. Let's see, 25 times infinity is going to be infinity, and the square root of a super large number is also a super large number, giving us infinity over 3. And a super large number divided by a tiny number like 3 is still going to be infinity. So therefore, as x approaches positive infinity of this function, the height of this function is also going to approach positive infinity. All right, so next up we need to take a look at limits at infinity of exponential functions. We have a theorem to help us determine the end behavior of exponential functions, and this theorem says that the end behavior for e to the x on the domain from negative infinity to positive infinity, all real numbers, is given by the following limits. So the limit as x approaches infinity of e to the x will then equal infinity, and the limit as x approaches negative infinity of e to the x will equal 0. And we can determine that these limits are true by looking at the graph of e to the x. So looking at the graph, we can see that as x approaches positive infinity, that the height of our function, or the end behavior of this function, is going to approach positive infinity as well. And then as our x values go towards negative infinity, we can see that the height of our function, or the end behavior of a function, is approaching 0. So we are going to use these theorems to help us evaluate limits at infinity of exponential functions. But before we do that, we have to do a quick, brief introduction into growth rates. Because when we solve these limits at infinity of exponential functions, we're going to need to know some basic information about growth rates. So what is growth rates, or what are growth rates? Growth rates refer to the rate at which y values increase or decrease as x approaches infinity. So our function that grows the least amount is going to be our linear function x. Yes, it does go to infinity as x approaches infinity, but it does so at a constant rate. From there, we know that x squared, the function x squared, increases faster. than x does, which makes sense. It should increase maybe twice as fast. Well, then x cubed would then increase quicker than x squared. And then we can make the case for all that being true for any x to the nth value where n keeps getting larger and larger and larger. And this is true for all polynomial functions. The higher the degree, the faster the growth rate is going to be. So now we have to think about, well, what increases faster than a polynomial? Well, the exponential function, turns out, increases faster than a polynomial, because whenever you hear about things growing rapidly, people often refer to it as increasing exponentially, or getting exponentially large, because e to the x represents that type of growth. It grows super fast. Now, is there anything that grows faster than e to the x? And yes, there is. There is this function known as x raised to the x power. We will not necessarily be dealing with that much in this course, but you'll dive into this information and you'll dive into growth rates further in Calc 2. But again, we just need to know basic stuff, such as e to the x grows faster than all of our polynomials. So with that in mind, we're going to learn how to evaluate limits at infinity of e to the x. Now, we technically don't know quite enough yet to evaluate limits at infinity of e to the x. So we're going to use kind of an intuitive approach here until we actually go over the material necessary to evaluate these properly. So this is going to be a little bit odd, but you'll probably like it better because it doesn't involve the rigor of mathematics. All right, so we're looking at end behavior here. And well, we can break this limit up to be the limit as x approaches infinity of e to the x minus the limit as x approaches infinity of 7x. Now, we know that if we substitute infinity into e to the x, it's going to equal e to the x based on our end behavior theorem that we talked about earlier. We also know that e to the x is going to be the fastest growing function that we talk about in this course. So therefore, to signify that e to the x grows super fast, I'm going to make this a really big infinity. And then minus, well then we have the limit of a linear function here, 7x, and we know that linear functions increase, but they do so kind of slowly at a constant rate. So to signify that, I'm just going to draw a itty bitty infinity there. So yeah, it does go to infinity, but it goes a lot slower. Now here's where it gets a little bit weirder. If we have a really big infinity, and we take off a really itty bitty infinity, we're still going to end up with an infinity. And yes, I know that in previous videos I said we can't do infinity minus infinity. It is an indeterminate form. And yes, that is true. We can't technically do this mathematically, but as I mentioned, we don't have enough tools yet to evaluate this properly. So for now, we're just going to be doing this kind of intuitive version of math. All right, so there we have it. The end behavior for the function e to the x minus 7x is just going to be infinity. Next up, we have the limit as x approaches infinity of e to the x minus 2x squared all over x squared. Now, if we would break this up and substitute in infinity, again, based on our basic growth rates, we know that e to the x grows the fastest. So I'm going to make that a big infinity. Minus, well, x squared, it does grow and increase, but it's a squared, it's a small degree. So it's just going to increase just a little bit. So I'll put a little infinity there. Divided by x squared is also a little infinity. Well, a really big infinity minus a little infinity is still going to be a pretty big infinity. Divide that by a little infinity. And well, a really big infinity minus a really little infinity, and it's just going to still be infinity because the numerator is still bigger than the denominator. So therefore, we're going to end up with a whole number of infinity. And finally, we have the limit as x approaches infinity of 4x minus 3 all over 7 times e to the x minus 2x. All right, so again, we said linear functions grow the least, so those would be itty bitty infinities. Minus 3 over, well, e to the x is a really big infinity, so we'll throw that in there. Minus 2 times a really itty bitty infinity. All right, so continuing our non-math math here. itty bitty infinity minus 3 is still going to be an itty bitty infinity. Really big infinity minus a little bitty infinity is still going to be a pretty big infinity. And in this case, we have a small infinity on top and a large infinity on the bottom, meaning that the bottom grows a lot larger or a lot faster than the numerator. And this is similar to when we talked about 1 over infinity. We said that that 1 over infinity approaches 0. And since we're taking the limit here, little infinity over super big infinity is going to have that same property of going towards 0. So whenever we have a bigger infinity in the denominator, it's going to approach 0. And there you have it, folks, a very intuitive version of limits at infinity for exponential functions. Again, we will be talking about how to evaluate these limits later on in the course when we actually have the tools to answer them. However, Newton just wants us to do a little bit earlier, so we'll do it.